Good morning, everyone. Welcome to Chemistry with Professor John. All right, we are doing stereochemistry today. Stereochemistry refers to the three-dimensional structure of molecules, okay? Just like an object, like a chair or a pair of shoes. Molecules have a three-dimensional structure as well, and so that's what we're going to be looking at. Okay, the a main goal will be classify molecule as chiral or achiral, meaning the term chirals mean handedness, like left-handed or right-handed, just like your shoe, right-handed shoe or left shoe. Okay, achiral mean not handed, like something symmetrical, like a folding chair. Okay, and identify the mirror plane of symmetry. That's the molecule has a plane of symmetry. Okay. Asymmetric carbons, that's the chiral carbon. And then we're gonna decide R or S, left-handed or right-handed, pretty much, And finally, looking at the specific rotations, the way the molecule rotate. Okay, now remember constitutional isomers, that's structural isomers. That's different in bonding sequence. Okay, meaning when you have butane and then you disconnect the last carbon and you stick it right in the middle, that will be an isomer. Okay, that's structural isomers. These two, and it's not butane anymore. It's 1, 2, 3. You can call it a 2-methyl propane. Okay, now we're not talking about, we're done with that, right? Now we're talking about stereoisomers. Everything is the same bonding sequence, only different spatial orientations of their atoms. Okay, so what are we talking about? Like, okay, so let's get to some definition first. Okay, the term chirality refers to pretty much handedness, left-handed or right-handed. If you have a molecules or an object and you got a mirror image molecules and they're not superimposable, meaning not stackable, then they're chiral. Okay, let's take a look at the example right here. So you have one molecules on the left and you have another molecules on the right. Now these two are mirror image to each other. Okay, you can see if you put imaginary mirror in the middle, and obviously the picture in the mirror is the molecules. Okay, now if you try to take one and stack on the other, you're not going to be able to do it. Like simple, you slide this over, that will be on the left side and that's on the right side, so they're not going to match. I mean, that's an easy way to think about it, right? So these two molecules are different. Okay, and we call them enantiomers. Now they're different not because they have different kinds of atoms. They all have chlorine, carbon, and hydrogens. They all have the same structure. The only thing different is this chlorine is on the right side and that is on the left side. That's it. That's the only difference. Okay, that's called spatial arrangement. So these two isomers, very special isomers known as stereoisomers, specifically enantiomers. Now, if we build this one, that's different, right? That's a trang. You see the two chloro opposite. Now, if we got the two chloros on the same side, then you can't tell which one's right or left. So you do the mirror image, and you can actually slide this over, and it's right on. It's stackable. It's the same molecules. So we're saying that there's only one because it's appeared as two, but there's actually only one. So we call that achiral, okay? And here's another example. You got a molecule, that's a carbon, okay, bonded to a methyl, ethyl, bromo, and a hydrogens. You do the mirror image, doesn't matter how you try to rotate, it's not gonna be the same. The mirror image and the original molecules, these are two different molecules just because of the way branches are organized, okay? Now, you can think about, just look at the bromo. On one side it's on the right side, and the other side is on the left side. So they're not going to match, okay? Unless you cannot tell the difference, right or left. Okay, so that's enantiomers, meaning chiral, okay? So a chiral molecule has a non-superimposable mirror image known as enantiomers. A chiral molecule doesn't have that, okay? It has a mirror image, but it's the same one. That's identical. A chiral compound or molecule always has an enantiomers, okay? A achiral compound always has a mirror image, but that's the same as the original molecules. Okay, so those are the things you want to keep in mind, okay, when we talk about chiral compound. Now, chiral compound, okay, how do we identify that, right? Carbon is a popular atom in an organic compound. So if we can identify the carbon, that will help. And that's the easiest way, okay, instead of doing mirror image thing. Now, it turns out chiral carbon is present in like 99%, 99.9% of chiral compounds, okay? Also known as asymmetric carbon or stereocenter or stereogenic carbon atoms. Okay, when you have a chiral molecules or compound, very likely you have a chiral carbon. Okay, so what's the definition of a chiral carbon, right? A chiral carbon, or any atom, doesn't have to be carbon, is the one that's bonded to four different atoms or branches. Four different: bromo, chloro, hydrogens, iodide. Okay, and the priority based on the atomic numbers. Okay, so if bromo has atomic number 35, that's higher than chloro, 17, but iodide has an atomic number 53, that's the highest. So in terms of priority, iodide is the first one. Not alphabetical order, it's atomic numbers, very simple. Iodide, bromide, and then chlorine, all right, or chloro, iodo, bromo, chloro. Hydrogen is the lowest one, okay? So keep that in mind, it's going to be helpful later when we assign the rotations. Now, nitrogen has only 3 bonds usually, but if you make it into a nitrogen plus, then it's got 4, and when it has 4, it's also chiral because it's bonded to 4 different groups. So not just atoms, 4 different groups. Okay, that's a propyl, that's an ethyl, that's an isopropyl, and that's a methyl. So those are all different. Okay. So it's chiral. You do a mirror image, you're not going to be able to stack them because the methyl is on the left side and methyl over here is on the right side. So it's not going to match. Everything else different, right? Okay, now if you have two groups on the carbons are the same, then it's not chiral. So if you have a methyl and you have another methyl, by the way, wedges bond mean towards you and dash mean away from you. If you got a C2H6, that's an ethyl. Now you got two methyl of the same, this automatically not chiral. And you can have like a Br here or whatever. Okay, or you have 2Br or 2Cl, not chiral. Achiral mean not chiral. Okay, so if a compound has, like this particular one has, there's no chiral carbon, very likely it's not chiral overall. All right, now, so what's the summary, right? If a compound has no asymmetric carbon, meaning no chiral carbon, it is usually achiral, the compound, okay? There's a couple exceptions. In some cases, like allene or the ring structure, they don't have any chiral carbon, but it is chiral, okay? Now, what we can know for sure is if a compound has just one chiral carbon, asymmetric carbon, it is chiral. If it has more than one, we have to see if they cancel out, the rotation cancel out or not. Okay, just like polarity. Okay, so we'll look at that example. Here we go. Now, if you think about this one we received it before. We got two chloro on the same side. Actually, if you look carefully, each carbon is actually chiral within the molecules. Well, this molecule has internal plan of symmetry. Now, you got the left and you got the right. Okay, so turn out they cancel out. So each carbon is actually chiral because it's got 4 different atoms or group bonded to it. If you got the one on the left, your chlorine is on the left, and you got the one on this, the chlorine is on the right. So it turned out they cancel out. So overall, it's not chiral, you know. If you do mirror image, it's going to be the same molecules. So this one is achiral. Same molecules mean achiral. Okay, and these are the same, you know, similar example. You got, okay, so two chiral carbon doesn't mean it's going to be chiral. Just like, you know, you have a CO2, you got two polarity, but doesn't mean it's going to be polar. They cancel out, right? So it's not polar. That's, I mean, the same idea. Okay. Okay, now remember I mentioned earlier about, there's one more example I want to show you, which is the 2 double bonds in a row. Now when you do 2 double bonds in a row, you do you do 2 double bonds in a row. The way you draw the structure is interesting, you know, because there's 2 pi bonds, one on the left of this center carbon and one on the right. Now they cannot be on the same plane because of the way the p orbital, the parallel p orbital overlap. Okay, so it's the middle one. So the second set of p orbital has to turn 90 degrees. So you got 2D on one side, you got 3D on the other side. So if you do So this molecule is actually twisted. That's why it is chiral. Chiral molecule with no chiral or asymmetric carbon. Okay, and that's because if you do a mirror image, you're gonna build a molecule. You build a molecule, a mirror image, and it doesn't matter how hard you try. Very simple. You're not going to be able to slide one over and stack on the other. It's always going to be unstackable. Okay, they don't match. All right. Now, and that's a good example of a molecule or a compound that is chiral but has no chiral carbons. All right. Okay, so let's move on. Now, how do we do a rotations, right? So we base on the atomic numbers, okay? Like iodine is high, And if you have like carbon, 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 how can you tell, right? You look at the next one. So the next one is Br, so it's higher than Cl. Doesn't matter how many Cl you have. And you always look at the next one. If you have double bond, obviously double bond is higher than single bond. Triple bond is even higher because it's triple. Okay. And then what you do, you put the lowest priority group in the back, and then you do rotations. Okay. And here's what I mean. So you got nitrogen is number 1 because atomic number is 7. Carbon atomic number 6. Now this carbon is number 2 because is has oxygens. This carbon is number 3 because it's only by itself. Okay, so 1, 2, 3, and hydrogen is the last one. Number 4 is in the back, always in the back. And you do rotations, 1, 2, 3, and that's counterclockwise. You call it S, right here. Counterclockwise S, clockwise R. All right, R, 1, 2, 3. Now if you do the mirror image, okay, then you get the one on the right is R, the one on the left is S. Yep, same thing for here. Okay, now we can measure that. There's a machine called polarimeters, and we hit the molecule with a light, plain polarized light. That's light that goes in this one direction. So what happened is the molecule actually will turn the light a degree, like rotate the light 5 degree, 30 degree, whatever, depends on the compound and the concentrations. Okay, so if you make a solution to make it simple, you can observe the angle and then you can calculate the rotations. Okay, but no, we're not going to get into that. All right. Now, if you have a mixture that has 50% of each if you have a mixture of 50% of each enantiomers, you get yourself a racemic mixture, all right? And what is percent EE, okay? So let's say you got 60% R. To make it really simple, of course you're gonna have 40% the other one, right? So your difference will be 20% EE, mean excess R. because 40% will cancel out. 40% R will cancel out with 40% S, you get extra 20%. So if you got 90% R, obviously you have 10% S, so you have 80% EE of course, and then 80% EE of R. And you can have the other way too. I mean, you can have 99% S, 1% R. You got 98% EE of what? S, right? So it's very simple. That's because they cancel out. So obviously, if you have 50% R and 50%, and sometimes people call it plus minus, different nomenclature, and then 0%, okay? EE mean racemic. So the mixture is not chiral because they cancel out. Okay, there's a couple of problems here for you to practice, and then we'll look at the quick summary and homework exercises. Identify if it's chiral or not, okay? And assign. You know, let's do a quick one here. This is chlorine, that's atomic number 17, so that seems to be the highest. That's a 1. And then that's a carbon, that's a double bonded, so that's 2. That's a methyl, 3, 4. So if you do a rotation, 1, 2, 3, 4, that's counterclockwise. So that should be S. Quickly on this one, you got oxygen. Ooh, that's the highest one. And you got a carbon with 2 oxygens. That's 2. Carbon with 1 oxygen. That's 3. And hydrogen is 4. Notice hydrogen is towards you, not away from you. It has to be away from you. The lowest one has to be away from you. Now, if it's towards you, the rotation seems to be clockwise, right? But because hydrogen is deceiving, it's towards you, so it's actually the other way. So it's actually is counterclockwise. So we're going to call this S. Okay. Because hydrogen is towards viewer, rotation is actually backward, meaning counterclockwise. So it's S, right? Okay. So I'll let you guys practice, you know, the rest of them, and we can check the answer later. Okay, cool. So that's first part of stereochemistry. Thank you for watching, guys. I'll see you guys next time. Have a good day.